of you was here with us last year? Show of hands. Yeah, half of it. Great, and many thanks for the many responses we got for the post-event survey. And of course, we looked through all of them and we took them very seriously. And one of the biggest and actually highest rated responses was that you want more deep dive tech content. And I think this talk is pretty much a prime example of how we made up this promise to be better this year. This talk is about raw dodging the proc file system. We have a seasoned fintech expert here. Aivars is actually coming all the way from Latvia, from Riga. He has dozens of years of experience as a software engineer, as a software architect, and I'm glad that he's demonstrating what you can actually do with the board capabilities of Linux by only exploiting the proc file system. Please give me a hand for this last talk in Hall 6.
Okay, so first of all, I'm a developer. Because I started some time ago, I also know a thing or two about SRE and database administration and other things. So I used to be a C and C++ developer writing software on these different kind of exotic Unixes. And we were a vendor, so we were supplying software to many banks, and then banks were running on their premises on strange enterprise-level machines. And so one of the things we had to do is to look for incidents and do troubleshooting on those systems without having access to them. And so most of what we did was over the phone and email. So we kind of learned to stick to some basic tools that most of operating systems have. So now I'm working for Ebury. So completely different environment, but again, so we are running in cloud, but normal developers do not have access to production. So it's again kind of half blind. You have to figure out why the software is not working. And then I do some other projects, and also I'm a bit involved in cybersecurity, so you might sense some security stuff in my talk. However, so how this started is we all have our own tool set that we apply to when we have to do some work, but oftentimes I have to work on systems where I don't have the luxury to install my own tool set and bring my own scripts and aliases and so on. So I'm interested more in fundamental things like how the tools that we take for granted, how they actually work. And surprise, surprise, they work through this process file system. So what's interesting about this is that when we think about Unix, we were taught at university that everything is a file in Unix. And this is kind of true nowadays, or true-ish. But the interesting fact is that the process file system, which means processes as files, was introduced only in '84, so in the 8th edition of Unix. So it's 10 and something years later since the first version of Unix. So it's not like it started off as everything is a file. And how do you explore this file system? You could read the documentation. You could go through the kernel source. The way I approach it is I have this tool called strace, which traces system calls into the Linux kernel. And then I tell it that I'm interested into these specific system calls that are related to files. So that's -e file. And then I launch whatever command I want to. So in this case, netstat. And then I look for a file name that starts with proc, and turns out that it reads a lot of files from the proc file system, like proc file systems, and then some netTCP files and so on. And then once I know which files it uses, I can go to the man pages and read more details about the files themselves. So that's the discovery process. Let's start by the kind of overview, the system level information. So probably the file we all have used before is the CPU info. So the most important thing there is the number of CPUs you have, and also sometimes the instruction sets they have. And it does the right thing, so it starts the indexing from 0. So I have 8 kind of virtual CPUs. In real life, I have 4 cores, and then each core has 2 threads. So keep in mind, so 8 CPUs, it will come handy. Now, so again, something all of us have used is the uptime utility, which tells how long the system has been running. And it gathers information from the uptime file on the process file system, and it contains 2 numbers. The first one is what we are familiar with, so it's number of seconds, how long the system has been up. In my case, it was something like 7.5 hours, because I had to do a restart. But the second number, it's a bit more interesting, because so the long description of it is that it's the idle time on each CPU. So it should be roughly equal to the first number multiplied by the number of CPUs, so 8 times. And since it's very close, it gives you the idea that I wasn't working hardly on this computer, so I was lazy. But it is what it is. And the same for the load averages. So we are used to seeing these 3 numbers, which tell like moving average over some minute, 5 minutes, 15 minutes, and so on. But again, there's more information into that. So I like the 4th number. So what it says, it shows it's 2 numbers divided by slash. So the first says how many processes are in a runnable state, so able to run on the CPU, and the second one is the total number of processes in the system, and the last one is the process ID of the last process that was created. So if I would, for example, keep track of this file, I could see which are the new processes being spawned by the system. But there are better ways how to do it. So again, something we all could be familiar with. This is proc version, so it actually displays the version of the kernel. So not much to say about this. And then there's meminfo, so information about memory. There are many fields about how memory is divided between caches, buffers, and then there are resident memory and so on. And if you are wondering on the first number, so the number of total memory in my system, so it's 40 gigabytes, so it's not a joke. And do you want to know how it's achieved? So the specific machine has 8 gigabytes soldered onto the main board, and then I inserted 32 gigabyte stick. So it gives you 40 gigs, so unusual number. And then, so this is the funny thing. While doing this investigation, like preparation of presentation, I actually discovered that I have a swap on the system. I never remember adding a swap file, but obviously at some point I did it, so I do have a swap, and you can find swaps in this proc swaps file. What's more interesting is that, so I started with netstat. So it looks into this specific file, which is under /net/tcp. There are similar files for TCP6 and UDP and UDP6. You can guess what it is. So it's the protocol. And it prints on the screen a bunch of gibberish. But if you look closely to it, so there's the local address and the remote address. Of course, the bytes have been like reversed in reverse order. So FE is 254. So, but if you are used to hex numbers, you can make it out that this is the source IP address and destination IP address. And there are some other numbers, but we will return to this topic a bit later, because there are some pieces of information I have not shared with you yet. So we have the TCP connections. And then so this is my personal project. I don't expect you to share the same passion for it, but I'm very passionate about System 5 IPC. So there are like message queues living in the kernel, and then there are semaphores and shared memory, and you can do a lot of things with them. And mostly nowadays they are forgotten, or some of them are replaced by POSIX alternatives of message queues and semaphores and shared memory, which do kind of the same, but they lose some of the nice features which are specific to this System 5 IPC. And the reason for that is I worked with the middleware that was using this System 5 IPC, so that's still my pet project. So there are many other folders which I will just skip because I won't have time for it. So let's go into the most interesting part about the process information. So under the process file system, for each process ID, there's a separate folder, and there are two links. So the self is a link to the PID of the current process, and the thread self is linked to the current thread. So in Unix, we might think that we have multiple threads, but in reality, those are multiple. So those are processes which just share the same heap and some other things. So they still have their own process ID. And yeah, so if you look, I mean, for some reason, the kernel developers decided to call it self. So I suspect there are hidden Python developers there. So it's not said, it's not called this, which would lead to C++, but no, it's called self. Knowing that there are processes, there's the folder for each process under this proc file system. You can monitor the creation of the processes. So there are several tools. The one that comes up the most is something called pspy, like process spy. So in the essence, this is what it does. So it lists all the process IDs that are currently on the proc file system, sleeps a bit, does another listing of the processes, and then sees which are the new processes, and then displays some information that, oh, this process has been started. So it's not the best way, because there might be very short processes that run in milliseconds, and this kind of script will not catch them. However, there are a bunch of solutions on the internet which do the monitoring like this. So I think there are better ways like ODD or BPF trace, eBPF. But yeah, it's a very primitive tool, but sometimes still useful. Now, under each process, there are a lot of files. So in this case, those are symbolic links. So /exe, it's a symbolic link to the actual binary that is being run. And so the way there's this read link utility in Linux, so it shows what this symbolic link points to. If you do ls -l, it will also work. And in the same way, there's a cwd, which prints the current working directory of the process, which also comes handy. I will return to this a bit later. But so these are two links, which are interesting. Now, keep in mind that the exe points to Python 3.12. So there's another file called command line, so which is what it says. So it's the arguments that were passed on the command line. However, it's encoded in this C-style string format. It means that strings are separated by binary zeros. And for that, I use this translation utility where I translate binary zeros to new lines. So each thing on the command line is printed on its own line. And here, notice that the program here that was specified on the command line is actually Python 3. So, but turns out that this user bin Python 3 is actually symlinked to user bin Python 3.12. So this gives you a false impression. This is the real binary. In a similar format, there's the environment of the process, where again, it's encoded in this C-style string encoding, where you have to replace binary zeros with new lines, and then you have access to the whole shell environment. So it's useful to me for two things. So One thing is that oftentimes processes are started through a bunch of shell scripts that sometimes take something from environment, something was injected through Kubernetes and some with different ways. And in the end, you kind of do not know what is the actual environment variable that the process got. So this is where you can see the actual values. And the second thing is, since this is a cloud-native conference, then the cloud-native way of working with secrets is passing them to environment variables. So whenever I'm investigating something, so I have two options. Either I ask someone, please reveal this secret to me so I can test the connection in some different way, or I can go to this environment file and see what the actual value of the secret is, so without asking permissions. So obviously, I go to this environment file. Then there's the process status. Okay, so the process status, again, it contains a lot of information. The things I find useful are the UMask, so it kind of gives you idea what permissions the files created by the process will have. Then the state is interesting, so what the process is actually doing. So this one is just sleeping. Another funny thing is the tracer process ID. So what I have found out, so whenever you attach a debugger to the process, it is written there in the tracer PID. And if you are tracing the process, oftentimes it will refuse to be killed. And on a busy systems, I have used this tracer PID to find what is the process ID of the debugger that I have to kill first in order to kill the process itself. You can see also the number of threads and also the kind of capabilities of the process. I think on the first day, it was discussed that there are some kind of extra permissions each process has. So this is also worth looking into. Now, processes, I know that Golang mostly builds static binaries, but a lot of processes still use shared libraries. And so there's this /maps file, which describes libraries and also binaries, and their locations in memory to which they are loaded. So from there, you can see, well, basically which libraries were loaded in the process. And again, this comes handy for the next example. So there's also, for each process, there's the file called mem, which represents the memory of the process itself. However, if you try to read this memory, first you will get permission denied, because in Unix, other processes, a process is not allowed to read other process memory. That's fine. I try to do like that with sudo, so the magic word. But again, it says input-output error. And the reason for that is that this /memory file represents the whole 64-bit address space. However, in maps file, we know that we can see that not whole of this address range is used. So what we get with using cat, we access unassigned memory of the process. So if we really want to access memory through this file, so what we have to do, okay, and a bit background. So probably the most interesting things will be stored in the heap memory. So here, I look in the maps file for the heap memory. I get the starting address, I get the end address, and then I can use some tools like DD. And I specify that take input from this memory file, skip to the specific address. So this $signs and braces, I'm using bash to decode hex numbers and make decimal numbers out of them. Then I say I will use block size of 1 byte, and then I calculate how many bytes are there in this range, and then store this dump. to temporary folder. And then for this specific example, I know that there are very secret password inside the application, but you can imagine that I could just look for strings and find out the credit card numbers or personal private information and maybe some tokens access keys to some other resources. So that's how you do it. There's also, these files are, yeah, if you want, you can take, go to this link, so it links to some other talk I did. So you can also use these self-mem and self-maps to mess up memory, even in memory-safe languages. So the specific example uses Python. So in Python, you kind of can do raw memory access. The language protects you from that. However, it doesn't prevent you from reading and writing some files. And since this self-mem is just a file, and you are in the same process, so you don't have permission issues, you can actually override the Python application itself, and this one removes some constraints and checks so that it makes the code pass. So that's a nice way how you can use those self-aliases for the current process ID. And then, so the binary typically loads some shared libraries, and the way how you know which libraries would be loaded, you typically do LDD -R, which means resolve all libraries, so it will traverse the whole tree of libraries and print all of them. So here it says that it wants to use libxpat, and it will come from /lib, GNU Linux, and so on. However, if we look into the maps file, we see that it has loaded the library with the same name, but from a different location. The question is, why did it do so? For that, we again have to consult the environment file. So I know that there are LD parameters starting with LD, which control how the dynamic library loader works. And if I look for this LD library path, which means a list of folders where the binary will look for libraries. So it has dot as the first one, and then dot stands for the current folder. And then if I go to the specific process and ask which is the working directory of this specific process, it tells that, oh, this is actually my own folder. So that's why it's picking up the library from my own home folder. So, but this is the kind of libraries that you know of. You could also have some extra libraries loaded, so it's not just simple. So here specifically, I know that I have loaded something called backdoor. And this backdoor, what it does, it intercepts the system calls and messes with the system. The question is why this was loaded. Again, I go to the environment file, and this time it's a parameter called LD preload, which means that before the program is started, this specific library will always be loaded, and then it can intercept whatever it wants. And then the question is, what is the application actually doing? Typically, you would use something like debugger for that, but I found out that you can do the same, well, something like really minimal using the process file system as well. So there are two files, and both of them have to be accessed as a root, because a process can read other processes' memory. So the first one is stack, so it prints the process stack, but it only starts with an entry point in kernel and then goes up into what the application is actually doing in the kernel. Here, I mean, if I ignore the system call name mangling, I see that it's waiting in something called wait for. So it's a function call that waits on another process. There's also another file called syscall, which basically it prints the syscall ID. So system calls in Linux are made by a number, not by a name. and then it prints the content of registers, which are used to pass parameters into kernel. And then, so the first parameter is actually the function ID. So if you go to the Linux kernel source, you can find those, or I like this page by Filippo. I don't know who he is, but he has a nice table of these numeric IDs, symbolic names, and then you can go to the manual page and see the description of the system call. And then you can do like decoding on your side. And so by just looking at the stacks of all processes, you can also do like kind of system-wide profiling. So it's kind of very rough, but sometimes it helps. And this is, again, a bit from the incident investigation, where I have to understand what the systems are doing. So normally what I expect the system to do is to be blocked in some, so blocking call is where the process enters the kernel and then it waits there, so it doesn't return. So I expect the systems to be, applications to be stuck on something called poll, select, or pselect. So this is fine. There are, for completeness, there are system calls to do physical write and or send some data to the socket. It's very rare that you see them. Typically, it's when you are writing to a damaged disk. So you don't see them, but they are there. Sometimes I see processes stuck in the accept system call, which, depending on how the application is implemented, it might be okay, but it's like 50-50. However, there are a lot of applications that get stuck in connect or read and receive from. And this is typically because they are using some libraries in higher level languages which do not implement a timeout. So yeah, typically if I see in those, I go back to the developers and look. So here, when you are trying to connect, please set a timeout, otherwise it might hang forever waiting for the connection to the outside. There's wait for system call that we saw, which waits on the termination of child process. And there's also the futex. So futex stands for fast user space mutex. And typically when I see processes inside this, they are either deadlocked or they are starving, like lock starvation. So they are waiting on a lock that some other thread is holding. But yeah, a lot of times it's just a deadlock. And then kind of process performance, what I found out that I don't know what's the reason, but a lot of Oracle DBAs, they build those strange tools which use process file system. So I use this one, OX tools, it's by Tanel Podder. So it's Estonian DBA, and he has like really, really interesting stuff. I discovered some of the process file systems parts from him. So there's a file called scheduler, sched. So probably the most interesting thing there is the number of context switches, and it's divided between voluntary switches, where application switches with a good reason, and the involuntary, where it's process scheduler just kicks the application of the CPU. And normally, so as an application developer, I typically try to minimize number of context switches, and if I see too many involuntary context switches, then it means some other application is preventing my application from running. There's also called scheduler stats, so this one is used by one of those OX tools, which shows for the process how much time has it spent on the CPU, how much it was waiting, and number of time slices run on this specific CPU. Because the process might be scheduled between CPUs as well. Limits file. So limits are, I find it's hard to get them right. So oftentimes you have to type ulimit minus, let's say, C and unlimited. But because processes get started from other processes and get started from some shell scripts, a lot of those can be lost. And again, I have to know what are the actual limits of the actual process. So most important things are the stack size. So in Linux, it's 8 megabytes by default. If you have a heavy multi-threaded application, 8 megabytes might be too much. I have found out that a lot of applications work fine with just a megabyte of heap size, of the stack size for thread. So that's an easy way how to cut down memory usage. What worries me here is that the max core file size is set to 0. It means if application crashes, it will not produce the core dump. So this is one of those limits which we typically look for processes, that it should be set to unlimited. Then max number of open files. So on Linux, it's quite small, so 1,000. If you are running some web server, you probably have to increase it. And then also the nice priority. It's something you can find out there. And related to the number of open files, for each process, there's FDE folder where it lists all the file descriptors it has. So file descriptor in Unix is just a number. And then all entries under this folder are symbolic links. So you can find out that some of those point to the terminal, some of those point to some sockets, some point to actual files on the disk. And that's because kind of everything is a file in Unix. And going back to the limit, so there's the technically correct way to say is that Unix has limit of the maximum file descriptor, not on the maximum number of open files. But because of this convention that it had of convention how it assigns new like file numbers, it's almost the same. But in reality, so it's the limit on the maximum value of the file descriptor. And so a lot of applications in Unix produce these strange errors because the operating system has just the error number and then the constant string describing that error, and you get some error saying that, oh, you are over the limits, and people oftentimes go and, oh, let's increase the file limit, but it's actually not related to that. How can you find out if the process is hitting file limits? It's just look at the last file descriptor that was assigned. So on the largest file descriptor, here is 39. The limit is 1024. So it's not hitting the limits. So it's hitting some other limits. Now going back to TCP connections. So one thing this netstat displayed was the PID of the process and the name of the process to which the connection belongs to. So the process ID is 12505, and it's SSH. How did the netstat find that out? So there's the last column in this netTCP file, which is called inode, and it's the specific number. How do you understand what it refers to? So you do this. You go through the file system, you look at each process, you look at each file descriptor, and if the read link for that file descriptor returns socket, and within the braces it has this specific inode, that's the process that owns the connection. And by the way, yes, netstat is doing exactly that, so it's going through every file of every process. And that's why sometimes it can be slow. And now, restoring deleted binaries. So there's a thing a lot of red teams do, or attackers do, where they start a process, then remove the binary, and if you run some scans on the file system, you don't find anything, and it seems safe, but it is not. So here I created a copy of sleep. I started it and removed the file, so it's not there. If I look at the process listing, I see that my sleep is still running. If I look at the process ID of that file, it says that, oh, this file has been deleted, so it's not there on the disk. But oftentimes we still have to restore it, and we can. So the way to restore it is to use cat. So what cat does, it basically reads out whatever is stored in this pointed pointed to by exe, and then it copies into a new file. So if you try to do something like cp or mv, it doesn't work because it's a symbolic link. It would just move the link, not the content of the to whatever link points to. So when we restore the file, we can double check that it's actually the same, exactly the same binary that was previously deleted. So that's how you can try to restore accidentally removed binaries or somebody or some binaries that were injected into your system. And in similar way, restoring deleted log files or reclaiming space. So I have an application which is writing logs to the disk. At some point, it has written close to 10 gigabytes of logs. And somebody wanted to reclaim the disk space, try to remove the log file. The log file is no longer there, but the disk space is still being used. So why is that? It's because within Unix, there is no concept of removing the file. Even the system call is called unlink. So what unlink does, it removes the file name entry from the folder, and that's it. And then the content of the file still stays on the disk until the usage count of the file goes to 0, and then it's cleaned up by the operating system. So there's no removal, there's just unlinking, making it invisible. So, but we can use that to delete log files and reclaim log space. So if we look at the open files by the process, we see that it says, yeah, there's this large log file and it's deleted. And in a similar way, as we did with restoring the binary, we can use this file descriptor as a file. So we can run tail on it and see what is being written right now to the log. Or we can, again, use cat to extract all the content of the file and store it somewhere else. Again, things like CP or MV will not work on that. And then if we want to reclaim the space, so we must get the usage count of the file to 0. So the easiest way how to do it is just to kill the process. And if you kill the process, suddenly the disk space is reclaimed. Oftentimes when I approach the system, I just look for all files that have been deleted. So here it's not actually like physical files, but for some reason is the Chrome is creating some POSIX shared memory files. I don't know why, and it's deleting them, but still, while the process is still using them. So, but I don't have time to deep dive into that. And then again, something that there's this fuser utility, which is not installed by default on Linuxes, which tells you which processes are using the specific file. You can actually do the same from the process file system, where you list all the open files and just look for the file of interest, and then you get the process ID of the application. And yeah, that's it. So it's fun. So go ahead and write some of your own tools. So I have written some of them that kind of combine pieces of information that I'm looking for, especially like restoring these deleted files and finding binaries that are running but deleted. So that's how I use it. So thank you. So that takes you to the slides if you want to try some of the commands or files yourself.
All right, guys, you want tech, you got tech. Any questions?
Hi, thanks for the amazing talk, really cool. I'm just wondering, where did you learn and find out about all of this?
All of this?
Most of it.
Yeah, well, some of that from kind of cybersecurity training, and then just exploring interesting applications using strays. So as a developer, I kind of know what are the system calls into a Unix operating system, and then I see a tool which provides something that I have absolutely no idea how it could get it out of the Unix. So I run strace, I see what it uses to get this information, and then look into it. And oftentimes there are some small bits, like on the uptime, there are some extra information that's not shown, but it's kind of interesting for me.
Really cool. Thank you.
Very interesting talk. Thank you for that. I was interested to know how your lib backdoor intercepts syscalls.
Oh, lib backdoor. Okay, so very technically, it doesn't intercept syscalls. It intercepts libc functions that make the syscalls. So because libc has is dynamically loaded, so it has this symbol table where it writes down that, let's say, open system call, that the name open is assigned to this address, and it depends on the library order, loading order. So if my backdoor provides name open first, whoever calls it, it gets to my backdoor first. And then inside my backdoor, I use, what was the call? But there's a call which asks, give me this symbol, the next address for this symbol. So, and the next address is typically the libc itself. So I can intercept, call original function as well, but I can, for example, log each of those calls and something like that.
Okay, thank you.
Some questions over there.
Hey, also thanks from my side, really interesting. One thing I wondered is, maybe you know that in the proc file system you have all the process information like you showed us, which makes sense. But then there's also stuff like CPU info, mem info, the uptime is all in the root of the proc file system. But that's not really process information. Why is that in there? Seems kind of messy, no?
Yeah, well, it was decision made, so not by me, before me. But if you go, so I pointed this to this Usenix paper where they announced the process file system. So what happened before the process file system was introduced, they used the basically debugger to attach either to the kernel itself or to the processes to retrieve that information. And so they decided, instead of using this unreliable debugger interface, which relies on knowing the specific address offsets inside the kernel, so they decided to put that information on the process file system. So yeah, probably it would belong under a different location, but it is what it is.
Okay, so it's like the typical historical reasons and backward compatibility.
I think so.
All right, thank you.
I think there was another question over at that side. Yeah, just turn it over.
Could you please send over?
Just like.
Hi, thanks for the talk. I would like to ask you, would you also be able to just open a TCP connection and make requests using the Linux file system or Unix file system?
Yeah, I mean, there's the way how you do it in Bash, but it's not proc file system.
Okay, thanks.
Any other questions? Yeah, we got one over there. I guess you're faster.
Are there any examples that you found while doing security consultancy that you can talk about? Interesting backdoors?
No. I mean, part of it is exercises like red-blue team competition, so it's yeah, for those, I just know that that's a kind of common trick people use, but obviously nowadays it's, I think most of people go into like kernel modules and eBPF.
Thank you.